We know how to find the potential field from the electric field intensity. Let's see how we can find the electric field intensity if we are given the potential field. Let's assume we have a voltage probe of length delta L, and this delta L can be adjusted. The reading of the probe is the potential difference between the tip and tail of the probe, VA minus VB. The relationship between the reading on the voltage probe and the electric field intensity is given by this equation. If delta L is small, we can assume that the electric field intensity does not vary over the range of our integration. So we can factor the e to the left of the integral, and the integral of dl from b to a is just delta L. So delta V is equal to minus the magnitude of the electric field intensity times the magnitude of delta L times the cosine of the angle between the electric field intensity and delta L. Let's assume we have some electric field intensity as shown, and I've drawn some equipotential surfaces, and let me label this one 10 volts, this one 20 volts, and this one 30 volts. And I try to keep the right angle between the electric field intensities and the equipotential surfaces. Here is our adjustable voltage probe, and the voltage drop across it, as we've seen, is minus the magnitude of the electric field intensity, the length of our voltage probe, times the cosine of the angle between the voltage probe and the electric field intensity. I've placed the voltage probe in the electric field and at a right angle to the electric field intensity at this point. The angle being pi over 2 radians, the cosine of pi over 2 is 0, so the voltage across the voltage probe will be 0. And of course, with the probe lying on an equipotential surface, the voltage drop across it will be 0. I'm going to now rotate the voltage probe such that this angle gets greater. Here's a plot of cosine of theta versus theta. The cosine function varies between 1 and minus 1. As theta becomes greater than pi over 2 radians, the cosine function becomes negative, reaching a value of minus 1 at pi radians, 180 degrees. As I rotate the voltage probe, the angle gets greater than pi over 2, and the cosine function becomes negative. So the voltage drop across the probe becomes positive. As the probe rotates, the voltage across it may do something like this: 0 volts, 1 microvolt, 5 microvolts, 10 microvolts. At this point it will be a maximum. Then it'll start decreasing, 8 microvolts, 3 microvolts, 0 microvolts. So when theta is pi radians, cosine of theta is minus 1, and we get the maximum value for the voltage drop across our probe. And that voltage drop will be the electric field intensity times the length of the voltage probe. Now let's decrease the angle to 0 radians. So cosine of theta is 1, so the drop across the probe will be minus the magnitude of the electric field intensity times the length of the voltage probe. So as we rotate this voltage probe, the drop across it is going to vary from a maximum of E times delta L to a minimum of minus E times delta L. And the maximum occurs when the voltage probe is pointing in the opposite direction of the electric field intensity, when theta is pi radians. When you get this maximum reading on the voltage probe, you can then find the magnitude of the electric field intensity. It's that maximum voltage reading divided by the length of the voltage probe. Let me define a unit normal to an equipotential surface as pointing in the direction of increasing potential. We saw that as you rotate the voltage probe around, when the voltage drop across the probe divided by its length is a maximum, you have the magnitude of the electric field intensity. That electric field intensity will be in the opposite direction of these unit normals to our equipotential surfaces. So the electric field intensity is the maximum value of partial of V with respect to L, and its direction minus this unit normal vector is opposite the direction of maximum increase of electrical potential. This function right here is called the gradient of the potential. So the electric field intensity is equal to minus the gradient of the potential. The notation we use to indicate gradient of the potential is del V, and this del is that del operator we introduced when we were talking about divergence. Now that we understand the concept of finding the electric field intensity from the electric potential, let's look at how you would do that in our three coordinate systems. As we saw earlier, the voltage drop across our voltage probe is minus the dot product between the electric field intensity and delta L. So let's look at the Cartesian coordinate system. Let's adjust the voltage probe so that it's of length dx and pointing in the x direction. So delta L is equal to dx in the x direction. The voltage drop across that voltage probe, delta V, we will call dV. Let's substitute for delta L and delta V. We have the dot product between the electric field intensity and a unit vector in the x direction, which will just give us the x component of the electric field intensity. We can solve for E sub x and find that it is equal to minus dV dx. We now adjust the probe to be of length dy in the y direction. The drop across it is dV. Again, we will substitute for delta L and delta V. We have the dot product between the electric field intensity and a unit vector in the y direction, which will just give us the y component of the electric field intensity. So we can solve for E sub y, and it's equal to minus dV dy. Similarly, E sub z is equal to minus dV dz. Now that we have the three components, we can write the equation for finding the electric field intensity from the potential field. Recalling the form of our del operator, we can see why we write the gradient of the potential as del V. Now let's look at the cylindrical coordinate system. We adjust our voltage probe to make it length d rho pointing in the rho direction, and the drop across it will be dV. So let's make these substitutions. So we'll have the dot product between the electric field intensity and unit vector in the rho direction, which will just give us the component of the electric field intensity in the rho direction. So the rho component of the electric field intensity is minus dV d rho. We now adjust the length of our voltage probe so that it's of length rho d phi in the phi direction, and the drop across it will be dV. Let's make these substitutions. We have the dot product between our electric field intensity and the unit vector in the phi direction, so that will just be the phi component of our electric field intensity. Solving for E sub phi, we get minus 1 over rho dV d phi. And the z component of the electric field intensity will be the same as we had in the Cartesian system. Now that we have the three components for the electric field intensity in cylindrical coordinates, we can write the equation for determining the electric field intensity from the potential field. Let's now look at the spherical coordinate system. We adjust the voltage probe to be of length dr in the r direction, and the drop across it will be dv. So let's make these substitutions. So we'll have the dot product between the electric field intensity and the unit vector in the r direction. That will give us just the r component of the electric field intensity. We can solve for E sub r and find that it's equal to minus dV dr. We now adjust the voltage probe to be of length r d theta in the theta direction. The drop across it will be dV. So again, make our substitutions for delta V and delta L. We'll have the dot product between the electric field intensity and the unit vector in the theta direction, which will just give us the theta component of the electric field intensity. So we can solve for E sub theta. It is equal to minus 1 over r dV d theta. We now adjust our voltage probe to be of length r sine of theta d phi in the phi direction, and the drop across the probe will be dV. Again, substituting for delta V and delta L. We'll have a dot product between the electric field intensity and the unit vector in the phi direction, which will just give us the phi component of the electric field intensity. And now we can solve for E sub phi. And we find that E sub phi is minus 1 over r sine of theta times dV d phi. So now that we have the three components, we can write the equation for finding the electric field intensity from the potential field in spherical coordinates.